right, so this talk is going to be more of a case study. I'm just going to present work by others, which is always a bit challenging. So the work is done by Nord Quantique, and then different work done by the University of Sydney. And the common thing is that both of them used our products. So I'll present their work. So before going to the main part, let me just mention something that I talked about yesterday in my plenary talk, but I'm not going to talk about today. And this is the concept and realization that we're always obsessed with gate errors, right? We always think about gate errors and we think about thresholds, but the reality is that errors don't exist just in gates, right? Errors exist everywhere, and we always like to think that everything is eventually Markovian, but it's not. Correlations exist and crosstalk exist, and these things are crucial when it comes to error correcting codes, because most of them assume that they are not there, but once they are there and once they are not expectedly there, you can get quite horrific results. And of course, when you have correlations and when you have non-Markovian noise, error suppression can use that. That's the hallmark of error suppression. You can use correlations, you can use structure in order to eliminate errors to begin with. You cannot handle completely Markovian errors, but that's the claim of fame of quantum error correction, and it's really the combination of the two that allows you to handle, first of all, the errors and prevent them from happening in the first place, make sure you have no correlations, and then you have all you need in order to act with quantum error correction and really clean all the things that you want to clean. But I'm not going to talk about it today. I'm actually going to go much lower and try to give you an understanding of what does it even mean at the pulse level to prepare an encoded state to execute a 2-qubit gate between two logical qubits. How hard is it, and what does it mean in terms of optimization and design? And this is something that many times at the high level, when we think about codes, we don't really think about these practicalities of how do we really implement these things. So I'm going to tell you about 3 cases. The first one is by Nord Quantique, where they used closed loop optimization to design a specific quantum error correction protocol, and then 2 works by the University of Sydney, where they used model-based optimization, robust one, to both prepare bosonic states and then also design universal gate set between these bosonic states. All right, so the last talk actually served me well, because I always presented the concept of bosonic code, but the main idea is that we want to encode information in some extra degrees of freedom that we have, and the main idea here is that we can trade physical redundancy with complexity in some sense. So the way to think about that is that instead of having just a bunch of qubits, we just have creatures with many more degrees of freedom, and in some sense we can use less of these creatures. And there are different modalities and architectures that you can do that. For example, the first that I'll show by Nord Quantique, it's a transmon coupled to a resonator, but in the second one by University of Sydney, this is a chain of ions, and the bosonic modes is just the vibrational modes of these ions. So the concept can have many different modalities, exactly like you know, that our more standard gate-based one can have that. And of course, one popular state is the GKP state, these kind of checkerboard states that define the logical qubit if you just prepare the right combination of bosonic states. So the first work that I want to talk about is from Nord Quantique, and the goal there is a simple question. They want to prepare GKP state and ask whether they can use quantum error correction to increase the lifetime of this state. So kind of in some sense very similar to, for example, the question that Google asked in their last demonstration. And they know how to do it quite well. They know how to prepare at least a GKP state quite well. So they have a transmon that starts in the ground state. They have a resonator that starts in the 0 state. And then there is a routine that is using these, if you want, kind of analogous to 2-qubit gates. These are these conditional displacements operations between the transmon and the resonator that can prepare some GKP state. And the quantum error correction that they used is an unusual one. So the idea there is that you want to create a self-correcting quantum error correction. So instead of having detection and then decoding and then correction, active correction, they want to design the environment, in this case some extra resonator that they add, in such a way that the GKP manifold is a steady state of this environment. So even if you leave the manifold, the environment will force you to go back to the environment. And of course, there's quite a lot of theoretical work. That's not a new invention. And there is a well-known protocol which tells you that, for example, if you have your auxiliary, in this case it's a transmon, this is the storage or the resonator, and then another resonator, which is the environment, you can just create this procedure. This is a single quantum error correction, and then the actual implementation, you encode your GKP state, and then you just do n rounds of your quantum error correction procedure. Now, one thing that you can notice is that there are different parameters that parameterize these gates, and in general, you need to set them in order to be optimal. So the advantages, of course, is that it accounts for photon loss, which is non-trivial, and it removes the need in detection, decoding, and active correction, which, of course, has a large price. On the other hand, it introduces some optimizable parameters, which can definitely, if they're not optimal, can give you unpredicted errors. And on top of that, it introduces quite a lot of these kind of analogous to Q2B gates, these control displacements, which are the most noisy operations. So each error correcting round introduced 3 such gates. So clearly you need, first of all, to have quite good control displacements, and you also need to know how to set all these different parameters in a quite optimal way. And one big challenge with superconducting devices in general is that we always have noise models, so we understand these systems, but the noise models are rarely accurate at the level that if you want to create things at the 999 level, they're good enough. If you just want to calibrate a gate to 85, 90% fidelity, probably you can do it model-based. The understanding of the system is quite good, but if you really want to push it to a few nines, with superconducting qubits, because of crosstalks, because of your the different understanding of the control system, sometimes you just won't have a very accurate model. So for that, we offer them a closed-loop optimization. So the idea of a closed-loop optimization is that you can optimize things without having any model. So typically there is a starting point. We don't start without any knowledge. But then the main idea is that you have some set of controls, in this case maybe some pulses or some set of parameters. You send them to the device, you measure, you do some analysis of your results, and you send it to some autonomous agent. Or if you want, you can call it some optimization algorithm. And the only goal of this autonomous agent is to decide what is the next set of controls that you want to send to the machine. And then you just go over this loop again and again and again until you converge, until the set of controls that you send to the device produce the results that you want. And what is this autonomous agent? Well, there are many different algorithms, right? It can be a Gaussian process, deep neural network, cross entropy, CMAES, simulated annealing, reinforcement learning. There are different kinds of optimization algorithms that are known to be black box optimization algorithms, and actually our product, Boulder Opal, support all of them out of the box, so you can just use them. So this is what they did. So they used, all right. So they used our black box to do 2 things. First of all, to do a pulse level design of the hard operations of these conditional displacements, but then they also optimize the parameters of the QEC. And the idea there is that this is your cost function. You have some set of parameters of your QEC, you run the procedure, and you just sample the phase space in several places, and then you just run it in a loop and trying to optimize this noisy and glassy optimization in order to get into the best set of parameters. And this is pretty much what they saw. So they saw that after they optimize the gates, if they just run it with the best parameters that the model suggests, they pretty much at break even. They see that the gain from running, in this case, 4 rounds of the QEC, just give you pretty much the same results as just preparing the state and let it just decay. But then when they optimize using the black box, which gives you some information that you didn't have because your model didn't predict that, then you can push beyond break even. The next demonstration that I want to show you is from the University of Sydney, where the goal here is to use a single pulse to prepare a GKP state. Right? So instead of having a procedure that includes many gates and many operations, you want to use a single continuous pulse in order to create an arbitrary GKP state, which you can choose exactly the kind of the flavor of the state that you want to prepare. Now, this is done in ions, right? So University of Sydney, they build ion traps, and they have chains of ions, and the motional modes of these ions serve as the bosonic modes. Now, unlike in superconducting qubits, ions are much cleaner and well understood. So the models that you have that describe the dynamics and the noise of ions are typically much more accurate. So in this case, instead of using black or closed loop optimization, we can use model-based optimization. So for that, we also offer an optimization scheme which allows you to define the different nodes of some graph that you want to optimize. So that means that you can define constraints that you have. You can define noise. For example, many times you know what are the noise terms, and you have some idea what is the structure of the noise, in the sense of what is the power spectrum of this noise if you have some correlation. So you can insert it as one of your nodes. You can have different targets. So for example, in this case, the target will be a specific GKP state that they want to generate. Of course, you have your actual controls, what are the functions that you control, and so on and so forth. And once you just set each one of these nodes, you can just let it run and optimize very hard optimization problems. And this is, all right, I'll get there. Okay, or maybe not. I think we have some crisis here. Okay, oh, perfect. So in their case, what they wanted is robust control. So what is robust control? Robust control is not just a control that will give you the state, it's also robust to your noise, in the sense that if you have a bit of noise and if parameters in your model slightly drift, which is something that happens, your pulse is still quite good. So in the context of the previous slide, in this case, which is a bit hard to go, this node is not empty. They know that they have some noise. They can insert that noise. They can even put in the power spectrum that they believe the noise fulfill, and then they task this optimization to find a pulse that is robust to this noise. So first of all, what are the controls? So they control two phases, this phi r and phi b. These are continuous function of times that you can control. If you want, this is kind of the shape of these two phases, and you can actually see that as you go on, the state that you are generating is slightly different, and in this case, this was the target state. So by the time that we end this pulse, we want to create this state. But then you can see what happens if you are doing it in an optimal way or in a robust way. So in this case, they ask it to be robust to detuning. Right? And because detuning is something that can drift with time, right? It can drift on a scale of hours. So maybe if you optimize that, you don't want to re-optimize it after an hour. You want to keep using it for, let's say, several hours or a day. And during that time, the detuning is going to drift. But even if not drifting, you can have fluctuations that detuning will drift. So in this case, they intentionally change the detuning and want to see what is the quality. So you see that with zero detuning, whether you do optimal or robust control, you get the same result. But as you start to create detuning, the optimal pulse will immediately start to show worse behavior, where the robust pulse is quite flat. Of course, at some point it will start to grow, but if you just have small fluctuations around this range, or if you have drifts which are around that range, these pulses are going to generate the same quality of GKP state. And the last thing that I want to show you is also from the University of Sydney, where in this case the task was to design a universal gate set between GKP codes. And actually that was the first demonstration of entangling gate between two GKP code words. So again, the same procedure as before. It's a model-based optimization. In this case, it's a T gate, a control Z gate, and also two other single qubit gates, pi over 2 or 90 degrees rotations around Z and around X. So this is the gate set that they wanted to generate. As before, there are two phases that for each gate that they want to find, and a bunch of real-life constraints that you always have in your experimental system, like maximum control bandwidth, some experimental filters. Whatever we design here eventually go through some filters that exist in the system, so you need to know that if you send this, your qubits will feel something slightly different. You have all kinds of edge values, which are probably some constraints of your control system, and this is what they did. So they just put all that into this graph-based optimization, and this is the output, just each gate and the type of control that you can have, and then they can do a process tomography, for example, on this 2-qubit gate, and they find that this 99% fidelity is not the gate fidelity that they found, but when they subtract the coherence component, they get above 99, which means that the limitation is not the control. In terms of control, they can pretty much create something that is perfect. Currently, the limitation is only the actual limitation, and as they'll improve the coherence time, at least from a control perspective, they'll be able to create gates that are at the coherence limit or coherence limit. Yes, and with that, I'll finish with another slide that I showed yesterday. So there are different phases in the development of quantum error correction, and we are now, I would say, in the beyond break-even, where we try to push for these demonstrations of single operations, encoding, decoding, single qubit or 2-qubit gates. And in this part, being able to control and manipulate and handle these extremely hard problems is crucial, and many times these things are hidden from the top-level discussion, but without them, we won't be able to achieve our tasks. So with that, I'll end, and thank you very much.